to Lecture 5, Part 2. My name is Jorge Young, and this is for college algebra, and this is equations in two variables. So we have quite a few objectives. The first one is we're going to go ahead and graph equations by plotting points. And then we're going to go ahead and find the intercepts from a graph. Then we're going to find intercepts from an equation. Then we're going to go ahead and test for symmetry with respect to the x-axis, y-axis, and the origin. And then we're going to know how to graph key equations. So the first thing is, what's an equation in two variables? Well, you've seen these before. So an equation in two variables is an equation that has either an x or y or an a and a b. So here we have x squared plus y squared equals 5. That's an equation in two variables. Here's an example of a graph that you might see, the graph of an equation that has two variables. So y equals 2x plus 5. You're probably more familiar with the middle two than you are with the first one or the last one. So now that we know that what's an equation in two variables, let's go ahead and determine if a point is on the graph. So if a point is on the graph, then that means that that point is a solution to the equation. So it has to solve the equation, and if it does, then it's also a point on the graph. So the first point that we have is 0, 4. The equation that we have is 3x plus y equals 6, or negative 3x plus y equals 6. So when x is 0, we get 4. 4 is not equal to 6, so therefore 0, 4 is not a point on the graph of this equation, and also it's not a solution to the equation. So the next one, when we get negative 2, 0, negative 2, 0 is in fact a point on the graph. And then the point negative 1, 3 is also on the graph, and it's also a solution to the equation. So here we can see that the 2 points negative 2, 0 and negative 1, 3 are in fact on the graph, and 0, 4 is not. So the next thing we're going to talk about is we're going to go ahead and graph the equation y equals 2x plus 5. So what you've done thus far is that you pick points, right? So I'm going to make x 0. So what happens when x is 0? So I go ahead and substitute, replace x with 0, I solve, and my point that I get is 0, 5. So what happens when x is 1? Again, I substitute x 1 for x, I get 7, so the point is 1, 7. We do the same thing for x when x is negative 5, and also when x is 10. Now, since this is a linear equation, we realistically only need 2 points. We need 1 point to know where we're at, and then 1 point to know where we're going. So then here we have our 4 points, and we plot those 4 points, and we get the graph of the equation for y equals 2x plus 5. Now the next thing is, we're going to go ahead and graph y equals x squared. And now this is not a linear equation, so you're going to need more than 2 points. And so the table here has quite a few points. And until you know a little bit more about quadratic equations, this probably might be the easiest way to do it. Later on, we'll learn about the vertex and some other things to make it easier to graph a quadratic equation. So y equals x squared. Here's a table of values. We have x, and then we have y equals x squared, and then we have the ordered pair x, y. So plotting those points gives us the graph of the equation y equals x squared. So the next thing that we're going to talk about are intercepts. And so when we have the graph of an equation, when and where it crosses the y-axis or the x-axis, that's what we call intercepts. So here you can see that where it crosses the y-axis, that's a y-intercept. And then the 3 points where it crosses the x-axis, that's what we call the x-intercepts. So here, in this point, then our x value is 0. And in these 3 points, our y value is 0. So here's an example, right? Let's go ahead and find the intercepts of this graph. So looking at this graph, we can see that we have actually 1, 2, 3, 4, 5. We have 6 points. So let's go ahead and do the y-intercepts first. So the first one is 0, 3. And again, like I said, that's when the axis is 0. Then we have 0, negative 4 thirds. And then we have 0, negative 3.5. So those are the 3 y-intercepts. And then the 3 x-intercepts are negative 3, 0. Again, as you can see, that the y is 0, 3 halves 0, and then 4.5, 0. So what are some steps in order to find the intercepts? So to find the x-intercepts or intercepts, if any, you just let y equal 0 and then you solve for y. And then to find the y-intercepts, you let x equal 0 and then you solve for y. Sorry, the first one you solve for x and the second one you solve for y. So here we have an example. Find the x-intercept and the y-intercepts of the graph, and the graph is y equals x squared minus 4, and then we're going to go ahead and graph it by plotting points. So the example doesn't quite do it the table, right? And so I'm going to show you is the actual graph. Now here you can see that if I let y equal 0, I get 0, negative 4. So that's my y-intercept. That's also what they call the vertex. And then if I make y 0 and I solve for x, I get negative 2, 0, and then 2, 0. So these should have been the first 3 points you plot. Once you plot the intercepts, then what you do is you try to find points on either side. So I go ahead and so what happens when x is negative 3, then I get negative 1 and 1. And then here, what happens when I let y equal 5, then I get negative 3 and 3. So this is probably an easier way to graph this particular equation. The next thing that we're going to talk about is symmetry. So the first thing is symmetric with respect to the x-axis. So the way that we know if a graph is symmetric with respect to the x-axis is that if xy is a point on the graph and the point x negative y is also on the graph, then it is symmetric with respect to the x-axis. And here you can see xy is on the graph and so is x negative y. xy is on the graph and so is x negative y, and then also for the third point. So if a graph is symmetric with respect to the x-axis and the point 3, 2 is on the graph, then what other point is also on the graph? Well, knowing that if xy is on the graph and it is symmetric with respect to the x-axis, then x negative y should be on the graph. So if 3, 2 is on the graph, then 3, negative 2 should also be on the graph. The next thing is symmetry with respect to the y-axis. So if xy is a point on the graph, then negative xy should also be on the graph. And here we can see we have xy, so negative xy is on the graph. xy, negative xy is on the graph. So if it's symmetric with respect to the y-axis and the point 3, 2 is on the graph, then that means that the point negative 3, 2 is also on the graph. And then the last thing we're going to talk about symmetry is symmetric with respect to the origin. So if xy is on the graph, then the point negative x negative y is also on the graph. And if that occurs, then it's symmetric with respect to the origin. So here we have xy, and then we also have negative x negative y. We have xy, and then negative x negative y. So if it is symmetric with respect to the origin and 3, 2 is on the graph, then what other point is on the graph? Well, negative 3, negative 2 would be on the graph. And here's a rundown, and I'm not going to go through them, but I suggest that you do write this down so when you take a quiz and a test, you have these points handy. So here's the graph. If it's symmetric with respect to the x-axis, it will look like that. So it's a mirror image along the x-axis. If it's symmetric with respect to the y-axis, then the y-axis is your mirror. And then if it's symmetric with respect to the origin, then the origin is your mirror. And now, algebraically, how do we do that? So these are some tests for symmetry. So in order to see if it's symmetric with respect to the x-axis, what we do is we replace y by negative y in the equation. We simplify. If we get an equivalent equation, then the graph of the equation is symmetric with respect to the x-axis. Now, y-axis. So what we do is replace the x by negative x in the equation. We simplify. If an equivalent equation results, then the graph of the equation is symmetric with respect to the y-axis. And then the last one is the origin. So in this one, you replace x and y by negative x, negative y. You simplify. And if we get an equivalent equation, then the graph of the equation is symmetric with respect to the origin. So here we have an example. So y equals x squared minus 9 divided by x squared plus 2. We're going to go ahead and test this for symmetry. So here's the x-axis. So we replace y with negative y, and it's not equivalent. So this is not symmetric with respect to the x-axis. So, and the reason being is because if we multiply everything by negative 1, so we end up with a positive y, we end up with a negative x squared plus 9 and then a negative x squared minus 2, so it's not equivalent. The y-axis, we replace x with negative x, and we see that in fact we end up with a equivalent. So this is symmetric with respect to the y-axis. So x squared is equal to, in parentheses, negative x squared. And then the origin, what we do is we replace negative y with negative y and x with negative x, but this is not symmetric, so therefore they're not equivalent, so it's not symmetric with respect to the origin. Here's the graph of the particular equation. As you can see, the y-axis is the red line, and you can see that it's acting as a mirror for this particular graph. So the next thing that we're going to talk about is y equals x to the third power. And we're going to go ahead and plot this by plotting points. So we're going to go ahead and find the intercepts, and then we're going to check for symmetry. So let's find the intercept. So when x is 0 and then y is 0, and then when y is 0 then x is 0, so then the origin is the only intercept for this particular equation. So 0, 0 is the only intercept. So x-axis, we replace y by negative y. Negative y equals x cubed is not equivalent to y equals x cubed, so it's not symmetric with respect to the x-axis. And then if we replace x by negative x, so y equals negative x to the third power equals negative x to the third power. That is not equivalent to y equals x to the third power, so therefore is not symmetric with respect to the y-axis. And then the last one is the origin. So we're going to replace x by negative x and y by negative y. So negative y equals, in parentheses, negative x to the third power, which is negative x to the third power. This is in fact, so negative y is equal to negative x to the third power is in fact equivalent to y equals x to the third power. You just multiply both sides by negative 1. So this is in fact symmetric with respect to the origin. And then, so here we have a few points, and then we'll go ahead and plot them, and the graph of y equals x squared is there. So here we have another equation, x equals y squared. We're going to go ahead and find any intercepts, and then we're going to check for symmetry. So again, the lone intercept is 0, 0, and the graph is symmetric with respect to the x-axis. So if you replace y by negative y, you get x equals y squared. So therefore, that's why it's symmetric with respect to the x-axis. So here are the points. Here's our intercept, 0, 0. So then we have a point on either side, 3 points on either side of the vertex, because that is the vertex. So some things that we tend to do is graph the equation x equals y squared. But what we're going to do is we're going to only let y be greater than or equal to 0. So if we restrict y to only being positive, either 0 or positive, then the equation x equals y squared can be written as y equals the square root of x. And the portion of the graph of x equals y squared is in quadrant 1 is what we have, and that is in fact the graph of the equation y equals the square root of x. And here we can see that the top portion is in fact y equals the square root of x. Now the bottom portion is just y equals negative square root of x. Alright, so we're almost done with this particular lecture. We have one more example to do. We're going to go ahead and graph the equation y equals 1 over x. We're going to find any intercepts and then check for symmetry. So checking for intercepts first. So if we let x equal 0, we obtain 0 in the denominator, which makes y undefined. So there is no y-intercept. Now if we let y equal 0, we get the equation 1 over x equals 0, which has no solution. So then we conclude that there is no x-intercept. So the graph of y equals 1 over x does not cross, nor does it touch any of the coordinate axis. So let's go ahead and check for symmetry. So we'll replace y by negative y. That gives us negative y equals 1 over x. That is not equivalent to the original. And then for the y-axis, we replace x by negative x. Y equals 1 over negative x is equal to negative 1 over x. That is not equivalent to the original. And then the origin, we replace x by negative x and y by negative y. That gives us negative y equals negative 1 over x. And that is in fact equivalent to the original. We just multiply both sides by negative 1. So this particular graph is symmetric with respect to the origin. So here we have the equation. We're going to go ahead and fill out this table. So when x is 1 over 10, we get 1 over 10, 10. When x is 1/3, we get 1/3, 3. and then 1/2, we get 1/2 2, and then 1, we get 1 1, and then if x is 2, we get 2 and 1/2, and then 3 and 1/3, and then 10 and 1/10. And then we go ahead and plot those points, and we end up with the graph of the equation y equals 1 over x. And as you can see, that it does not cross, nor does it touch the x or the y axis. And that's the end of lecture 5. Thank you.